All right, so with politics in 1970, there were 160 African American women in elected public office in the United States. By 1993, that number had increased to 2,332. Write a linear model for the number of African American women who held elected public office at any given time between 1970 and 1993. Then use the model to predict the number of African American women who will hold elected public office in 2010. All right, so this is taken from some data update there. This is from your book as well. So let's go ahead and look at the dates. First thing we want to do is get a rate of change that's happening here. And remember that's your rise over your run or your your dependent variable over your independent. Remember time is always independent. So your y2 would be your 1993. Subtract your x1, sorry, 1970. Time is independent of everything. So that's our bottom one. Our top will be the ones that match with it. So x2 matches with y2, which will be 2,332. So hopefully you can see already that the y is representing the number of women, hashtag women. So number of women, and x is going to represent our time or years, time in years. And you could use t if you want there, t and x, t or x, and then xy. All right, so 2,332 subtract 160 will give you the rate of change of African women, African American women that served in office. So for the top one, we have 2,332 subtract 160. So that's going to give us 2,172 divided by 1993, I think it is, right? 1993 subtract 1970. That's a period of 23 years. And when we work that out completely, if we divide 2,172 by 23, we're going to get approximately 94.4. So we're going to have to approximate that with the approximation sign. So 94.4 African women. I'm just going to put women per year. That's how it increased. Approximately 94 people per year were being added. That's what the slope means, the rate of change. Now that we've done that, we have to write a linear model for the number of African women who held public office at any time between those dates. So, remember, rate of change is always next to your x value. So, if it helps to write this out, the number of those in office, number in office, is going to be equal to your rate of change, right, which is your slope, times the x. So rate of change times the number of years, uh, number of years, remember years is your x, plus whatever your starting number was. And that was in 1970. I'll just put start. Starting number. Okay, so let's go ahead and fill that in. So a number in office, I'll just replace that with an n. So our capital N is going to be equal to, and so our y is n in this case. So our y, I like y's. So our y is going to be equal to rate of change, that's your m, x plus b. Right, so what is your slope? 94.4 approximately. And you could use t and n if you want, n for number, t for time of years, plus your b, which was your starting point. Well, that was the amount of people you started with, was 160. All right, so if we go ahead and graph this on a Cartesian plane, we get a great idea of where we're starting at. Now, we're going up to a pretty high number there. So we're going to have to really work with this. And once again, I don't have the graph paper yet, so I made all these videos at once. But next time I have a graph paper, one like I did in one of the questions, it'll make it easier to see graphically. So remember, we're going to just graph this. And if you have a graphing calculator, you could do that as well just to get a general gist. But we do have our model, but we need to now graph it so we can predict the number that would be in 2010. Now there are 23 units here, so we're not going to go by ones. We could go by tens. 10, 20, 30, 40, 50, that would fit. So 10, 20, 30, 40, 50, 60. And that's because 2010 is 40 years away. So if 1970 represented the zero or the origin, this is the point we're looking at. 40 years from there would be 2010. Okay, so now that we know how far we're going on our x-axis, we need to graph out y. 1993 was at 2,332. So we can kind of predict that it's going to be pretty high because that's about 23 years. So yeah, it's going to be pretty high. So let's go ahead and go by thousands maybe. 1,000, 2,000, that should work. Let's see, 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. I don't think it should go higher than 6. All right, so this is going in thousands, so that's 1,000, 2,000, 3,000 as we said before, and just writing these out. All right, so remember down bottom is years, and the starting point was since 1970, and then on the right side is the number of offices. Okay, so let's go ahead and graph that. If you use our slope-intercept form, 160 is going to be really low. 500 is about here. So 160 is going to be like almost touching. So it's starting at like really, really low. Here, let's change the color so it stands out. So that's about 160. And these are estimated graphs, so our graph might come out at an estimate. But if you're using a graph paper, it should come out even better. And we can always verify it by substituting the x values into the y. X values to find the y. Alright, so we're going up by 94.4. Well, that's going to take some time. So if we're going to go by 40, we're just going to substitute in there. This is pretty long, so we're going to use our brains here. If I substitute x into my equation here, 94.4 times 40 plus 160 is going to give me my y. And that way we get something accurate. So 94.4 times 40 plus 160, that's going to be 3,996. All right, so that's an alternative way to do that. 3,996 is going to be approximately here. And you can see that lines up with 160. Just to do like another number, let's say we wanted to do at 23, right? 23 years would be about here. And we see that 23 was at 2,332. Because we're approximating, we might not get the exact same number. We approximated at 94.4. So it'd be pretty close, but not exactly. So 94.4 times 23 plus 160. So we're just a slight bit off. The book gives it to us, the calculator gives it to us as 2,331.2, but that's because we rounded that number. And so 2,300 would be about here, and we could draw a line through that. And we could use that line to quickly predict faster than we could if we actually did the calculations in a calculator. And so remember before we could just say if it's 3,000, we could match it down. Now these are not accurate. Your graph paper would be more accurate than this. But let's just say your accuracy is off. If you are sketching, you can always substitute. And that's the beauty of knowing the connection between mappings, tables, graphs, and whatnot. But remember, have graph paper for the next lessons, I will make sure I have graph paper that really allows us to match better. All right, so the other and last thing that we're going to do is what we call direct variation. Now, direct variation is basically understanding how slope-intercept works. It's just basically saying that it varies directly. As you increase one value, the other one increases similarly. You'll learn about this some more. We're going to learn about inverse variation. You might have learned this in Algebra 1. And so basically, it's written in the form y equals to kx. You notice that's very close to y equals to mx. So your k, which we call the non-zero constant, is said to vary directly with x. And you might have saw that statement in the very beginning of functions. I had used the inverse, directs inversely, I think I written. All right, so basically if you see this, it just says it's a direct variation. So let's just show an example of what this looks like. The variables x and y vary directly where y equals to 5 and x equals to 3. First thing, we want to write an equation that relates the x and the y. And the way that we do that, we just use y equals to kx. And we're looking for the constant first. So if y equals to kx, we have 15 for y. We don't know what the k is yet, but we do know x. So we just need the constant, so we just divide both sides by 3. 15 divided by 3 is 5. So that's my constant, k equals to 5. So then if I was to rewrite a general equation that I can graph, then my y would be equal to k. X would be written as y equals to 5x. Now that is slope-intercept form. So I can quickly graph this on a graph. 1, 2, 3, 4. Hopefully I don't need to go higher than that. We have 1, 2, 3, 4, 5. Remember, do this on graph paper. All right, so our y-intercept is 0. There's nothing there for the y-intercept, so 0. And we're going up 5 units and over 1. And so it's a steep graph, and that thing just goes up like that. And that would be our graph, right? And then for part B, they just want you to use variation. Sometimes you see this a lot. They want you to find y, right? So we're using this when x equals 4. And very straightforward. Just substitute like we've done in the past. This 5 looks a bit 3-ish. So y equals to 5 times 4. So y would be 20 when x equals 4. And that's it. You're done with variation. All right, so the last thing we want to do is just to see if something's in direct variation. Sometimes they give you a table, and we kind of touched on this before when I did tables. You're basically looking for consistency to see if there's common multiples. Now notice you don't have to substitute the x in and get a y. It's already there. You only need to see if there's a constant or common multiple in between the two. And you could do that by dividing the two terms. It doesn't matter which one, as long as you see a pattern. So we could say 16 divided by 288, but generally we say 288 divided by 16. And in doing that, what happens is you can determine whether or not they're the same. So generally we say y divided by x because that's how we write slope, right? Y over x. So 288 divided by 16. If we get a common multiple each time we divide these, then we know it has direct variation. It's just basically saying it's being multiplied by a common multiple, which is our slope. So let's see what 288 divided by 16 is. 324 divided by 18. 360 divided by 20. By the time you get three of them, you know you're right. So 288 divided by 16 is equal to 18. 324 divided by 18 is also equal to 18. And then 360, and you could do this one quick, cancel out the zeros. 36 divided by 2 is 18. And you could keep doing that, but once you get 3, you know you're in the right track. So because they all have the same common multiple, it means you have y equals to 18x. Right? 18 times 16, 288. 18 times 18, 324. 18 times 20, and so forth. So this one is indirect variation. So yes. And then the second one, you could do the same thing. Divide each one, y over x. So 2250 divided by 0.5. See if it equals to 3430. If it fails once, the whole thing is off. All right? And so you can see already, this one's supposed to be equal to 1. And this clearly is not going to equal to 1. So we don't even have to do that. 3,430 divided by zero point 0.7 will not equal to 6,400. I put 1. But just to verify it, you could try it out. 3430 divided by zero point 0.7. This actually equals to 4,900. And 2250 divided by zero point 0.5, that's half. Divided by half is 4,500. So these are not consistent. This one is not indirect variation. You could not write it this way.